Hello.
Hi, Harry. Oh, I'm having a bit of trouble here with getting rid of some stuff I have at the bottom of my screen. Oh, come on. I'm going to have to restart something. Hang on. You don't need to go anywhere. Okay, Harry, what questions do you have?
It's mostly just with the electron configuration ionization lab.
Okay. Yeah, that's a one where you have to do a lot of thinking.
Yeah, the web elements and all that.
Let me open it up.
It's more of a kind of what do you mean with that instead of a how do I do it type
I
of
got you.
questions.
Okay, so I'm taking a look at it. So where's your first, what do you mean?
It's the second question. I'm just stuck on what do you mean by with like equivalent?
What pattern, what does this pattern roughly fit? Oh, does this pattern roughly fit what is expected if the two electrons are equivalent? So above, when I talk about equivalent electrons, those are electrons that are basically the same distance from the nucleus. Okay, so those are equivalent electrons.
Oh. All right. Because we're looking at the one for helium, they're both like different numbers. Is that
They're
and they're
different
both
quantum
like different
numbers, but they're
graphs?
both in the first shell.
Oh,
And they're both in an S subshell.
oh, right.
So technically that means they're equivalent because they're the same distance from the nucleus, right?
Oh, right. Okay.
Whereas a
Yeah.
1s versus a 2s, they would not be equivalent because 1 versus 2.
Oh, okay. That makes sense. All right. There's that one, and then the other one I had was 7. I didn't
Okay.
really get what you meant with that one.
By now, you know that each set of ionization energy represents a shell. So did you map out the ones for neon?
Like the graphing it?
Yeah.
Yeah, I think so.
Okay, so can you show me what you have?
Oh, actually, no, I didn't actually quite do it just yet. I was going to, but I forgot,
Okay.
which was my bad.
So do you
I
have the
did.
10 do you have the 10 numbers?
I should.
Now
Oh
you
wait,
don't need them to the ones. If you round them off to the hundreds, like I
right?
think the first one would be 2100 instead of 2080.
Oh, right.
If you round them all off to the hundreds, it's easier to graph.
Oh, I didn't think about that.
But let me show you what you get in general for neon. So am I sharing what I'm writing with you?
Yes.
Can you see that? So for my graph, since there's 10 electrons, I want to make sure that the x-axis is goes from left to right 10. If this were helium, I'd put a 1 right here where the 5 is, and I'd put a 2 where the 10 is, just to make sure I use the whole space. Does that make sense?
Yep.
Now, the biggest number is around 130, right? 1,000?
Yeah, it's about.
Okay, so that's 130 up there. So midway is about 65. And half of 65 is about 32. Okay, and so if you look at 1, 2, and 3, and you look at 32, here's 16, here's 8, here's 4, here's 2. There's the first one, right?
Right.
And the second one is around 4,000. So there's the second one. And the third one is around 6,000. If this is 8, this is 6. So here's 6. And the next one is around 9,200. Is that right?
Yeah, it's about 90. Yeah, 93.77.
Okay, 9,400. And the next one's like 12,200.
Yeah.
So this is 16. This is 8. So 12,000 is kind of in between the two. And then the next one is what, 15,000 or 14,000 something?
Like 15,200.
Okay, so here's what you get for the next 3. And then all of a sudden it jumps to what?
20,000.
20,000. So if this is 32 and this is 16, then this would be halfway between 16 and 32, which would be 26, 24. This would be 24. So 20,000 would be somewhere around here. And then the next one is something like, I don't know, 25?
It's 23.
23. Okay, so that would be around here somewhere. Okay. And then lastly, you get 2 numbers that are really big, way up here, right?
Yeah.
Okay. So by now, you see that each set represents a shell. This is the second shell. And this is the first shell. So this is a set of numbers and this is a set of numbers. And so that's what I mean by now you know that each set represents a shell.
Oh, okay.
And here, we know the electron configuration of neon is 1s2, 2s2, 2p6, right?
Right.
So which electron is this guy? If we draw this out and do an orbital box diagram, so you see each arrow there, right?
Right.
This first electron, which arrow is it?
Oh, is that the first one, the up one on 1s?
No.
Oh.
Remember, the 1s is closer to the nucleus. That means it's harder to take, right?
Oh, right.
So which one is this?
Would it be, well then, if that was at 1s, would it be one of the ones in 2p instead?
That's right. And it doesn't matter which one you take. So the way I usually do it is last one in is first one out.
Oh.
So what would be the second one?
So would that be the up one on next to 1?
No, it wouldn't. It'd be this one.
Oh.
And the reason is because this one that is left over after the first one is taken, it's in an orbital by itself.
Oh.
These two are in an orbital together.
Oh.
Now, those electrons repel one another. So wouldn't it be easier to take an electron that's being repelled by another electron than to take an electron that is by itself?
Yeah.
Yeah. Because, you know, the other electrons help and push the other one out the door, so to speak. So it's easier to take. So what would be number 3?
Oh, so 3 would be the other down arrow.
That's right. And then what would be number 4?
Oh, would that be the up arrow next to 1?
That's right. What would be number 5?
And then that would be the up arrow next to 2.
And what would be number 6?
6 would be the up arrow next to 3.
Okay. And what would be number 7?
Would that be the down arrow on 2s?
That's right. What would be number 8?
And then would 8 be the down arrow on, oh, it would be the up arrow on 2s.
That's right. And the reason you pick the up arrow on 2s instead of the down on 1s is because the 2s is less stable than the 1s.
Oh,
Okay.
all
So
right.
basically you pick them apart by subshell first, then you go to shell. So here we're doing subshell first, then we're going to go to the next shell. So 9 and 10. Are you with me there?
Yeah.
Okay. So are the energies of shell closer together for large N or for small n? That's number 7. Oh,
Yeah.
this is for neon. So what we would have to do is we'd have to look at calcium. Did you graph calcium?
Oh, no, I didn't end up graphing that one either.
Okay, well, here's how calcium looks. Let me
I do
do
have
you a
the
favor
numbers
and
for
show it to
calcium,
you, all
but
right? I actually have it saved somewhere in a file.
oh,
You can look some of these things up on the internet. And
that's
so
true.
this one, actually, let me show you how I get it on the internet. So what I'm going to do is I'm going to share my desktop with you. And I'm going to put Web Elements. Web Elements used to have these, but they don't anymore. So some people have downloaded these files and they upload them to the internet, so you can find them sometimes. So Web Elements, Ion, since this is an English site, they spell ionization with an S.
Oh,
And then I'm going to put calcium. And then I'm going to go to images. And can you see this one right here? This is the one for arsenic
yeah.
right there. Well, we don't want that one. And it shows only the first 6 for arsenic, not all of them. So we want to find the one for calcium. It should be around somewhere. Now, sometimes when people upload these, they don't upload it based on it being an English site. They upload it based on they're an American. So how do Americans spell ionization?
Is it with a Z?
Yeah, with the Z. However, I did find it here, and here's calcium. Oh, shoot. Cancel. So let me get into what I'm trying to do is get this guy to be larger, but it's not working. So let me go into my downloads. Find the file and I'll open it for you.
All right.
I'll change my share in just a moment. So this is labs. This is ionization energy. And here is calcium. Okay, now I'm going to change my share so you can see what, actually, can you see it?
No, I'm still looking at the images.
Okay, so I have to go to a new share. So here's calcium, and now I'm going to zoom in on calcium. Now, it doesn't matter that you can't read the numbers very well. That doesn't matter one bit. How many sets of numbers are there?
20?
Pardon me?
20?
No, not how many numbers, how many
Oh,
sets.
how many
Where it looks
sets?
like the numbers belong together. They're kind of a pattern.
Oh, what is it? 2 sets? I
Well,
can't really.
look at these two at the bottom. Do they really look like they're the same? You see how there's a jump from 10 to 11?
Oh, right.
Isn't that
Oh,
distinct?
yeah. Oh, what do you mean like the? Oh, so what would it be? 10, 10, 8, and 2?
So it looks
Is that
roughly
kind of what
like
you mean?
this. I've exaggerated it, but so actually, let me do this real quick.
Right.
I'm going to trace it.
Oh,
What I'm doing is I'm putting a piece of paper on the computer screen
right.
and I'm just tracing it. So this will take just a moment, but once I trace it, you'll see what I mean, I hope. Okay. So let me share what I have with you. Okay.
Oh.
So here's what I have. It basically looks like this. And what I'm asking you to kind of see is that these two are one set, these are another set, and these are another set.
Okay, that's right.
So there's 3 sets there. Okay, now let's look at the electron configuration of calcium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Did I get that right?
For calcium?
Yeah. And how many of these have we got here? Let's see. So let's take a look at these together. And this is kind of hard to see, but oh, they only show 20. Calcium has, okay, calcium does have 20. Okay, so here it looks like there's 1 set, 2 set, and 3 set, right?
Right.
But if we do this, 1s, 2s, 2p, 3s, 3p, and 4s, and put all the electrons in, let's do the same thing that we did before and assign numbers to each of these electrons. Okay, so what do you want to assign number 1 to? The easiest electron.
Would 1 go to the down arrow on 4s?
That's right. Number 2.
And then would that go the down arrow on 3p?
No, go to the up arrow.
Okay, go to the up arrow.
So 4s are easier than 3s.
Oh, and then would 3 go on the down arrow on 3p then?
Yep. How about 4?
Oh, 4 would go on the other down arrow on 3p.
How about 5?
That'd go on the other down arrow.
How about 6?
And then 6 would go on the up arrow next to 3.
How about 7?
7 would go next to 4. Oh,
how about 8?
5. Oh, 8 would go next to 5.
How about 9?
And then would 9 down arrow on 3s.
10.
And then 10 would go next to 9.
Okay, and then
11 would go on the down arrow of 2p. Then 12 would go on the other down arrow. And then 13 on that. And then 14 on the up. 15, 16, and then 17, 18, 19, 20.
Okay. So if we look at the numbers here, this guy is number 10. This guy is number 11. This guy is 19, and this guy is 20. So what are these 2 electrons?
Was it 1s?
They're the 1s. What are these 8 electrons?
Is that, that's 11. Would that be what, 2s and 2p?
The 2s and 2p. What are these?
And then would that be 3s, 3p, and 4s?
3s, 3p, and 4s. So when I ask you our energies, because this is energy, right?
Right.
Is the 1 closer to the 2, or is the 2 closer to the 3, or is the 3 closer to the 4? To me, it looks like the 3 and 4 are really the same type. Don't they look like the same type?
Yeah.
So that means these are really close. But when we look at 2 and 1, they're not close. Right?
Right.
So are energies closer together for large N or small n?
Would it be large N?
Large N. And what did we find out from the hydrogen lab? When we looked at energies and we did this. Remember when we did this? N equal 1. And that was negative 2.2 times 10 to the minus 18. And then N equal 2 was right here.
Oh, yeah.
And N equal 3 was right here.
Oh, yeah. And then
N equal 4. And then it got really crowded, right?
Right.
So here, I asked you the question also, are the N closer together for are the energies closer together for large N or for small n?
That was large N.
Okay, and what do we find here?
And then we found that large N was closer as well.
So it's the same either way.
Oh, okay.
Okay. So this happens to be just another way of kind of looking at this type of thing.
Oh.
Okay, so here, the best way to figure out how many, N there are is to actually count electrons and look at the electron configuration. You can figure it out. And the reason you have to do that is if you have a 2 and a 1, it's easy to see they're different. Is that clear?
Yeah.
2 and 1, they're obviously different.
Right.
And 2, 3 and 2 are obviously different. Take a look at this 2 or this 3 and take a look at this 2.
Right.
They're obviously different.
But then
now, I didn't grab this one too easily. Now, what about a 3 and a 4? Is it easy to tell they're different?
No.
Now, I'm going to do a new share so that you can see the screen again that has the electron or the ionization energies. And what I'm going to do is I'm going to try and zoom this in even more. And actually, can you see my...
Yeah, I can see a little cursor.
Okay, so can you see that these two right here seem to be a little bit different than the following 8?
Yeah.
There's a little jump there, correct?
Right.
Okay, and so here's another interesting thing is if you take a ruler and you draw a line between the dots that are related to one another, you'll find that it intersects the origin.
Oh.
So can you see how a line through these 2 dots would intersect with the origin?
Yeah.
Can you see how a line through these 8 dots would intersect with the origin?
Yep.
And can you see how a line through these 8 dots would intersect with the origin?
Yeah. Oh, yeah.
And even, oh, darn it.
Oh.
And even with these 2 dots, oh, darn it. I got to do something real quick here. I'm having problems with my Elmo. It thinks when I'm trying to zoom out that I'm really trying to, oh gosh, where is it? Okay, so hopefully this will work. Okay, can you see how these 2 dots, they actually intersect with the origin?
Yeah.
Whenever that happens, whenever the dots kind of intersect with the origin, that means that they're similar.
Oh.
And the reason for them being similar is that it has to do with the idea that if they are similar or equivalent, they're about the same distance from the nucleus, right?
Right.
And if we take a look at a helium atom, and now I've got to change my share again. So I'm going to flip this over here, and we're going to look at a helium atom, which is 1s2. If you look at the numbers for helium, you get something like this. Here's 1 and here's 2. Oops, I haven't completed my share. I'm sorry.
Well, that's okay.
Okay, so here's my helium. So this is 0, this is 1, and this is 2. And they roughly go back to the origin. So that means that these guys are related. And they're related because they're both a 1s. And here's the deal. When you look at the energy, roughly speaking, it's proportional to the charges of what is separating. So for number 1, you have this. The very first one, you're taking it from a neutral helium atom, and you end up with a +1 and a -1, right?
Right.
So the charge is proportional to +1 and -1, or -1. And negative means that this is exothermic, but really we need to look at it as being endothermic, because really I should say it's negative here. So that'd be plus. Now, in the second case, you already have one electron taken. So we end up with a helium-2 plus an electron, correct?
Mm-hmm.
So for ionization energy 2, it's going to be proportional to +2 times -1 and the negative of that, which means a +2. So ionization energy is going to take one part of energy. Ionization energy 2 is going to take two parts, twice as much. Are you with me there or not?
Sorry, I was writing it down. Could you repeat it again?
So what I'm looking at here is that the energy to take the first electron, if we give it, assign it a value of 1, the energy to take the second electron should be twice as much. So we give it a 2.
Oh, okay.
If they're equivalent. But what if they're not the same distance from the nucleus? And the answer is, if they're different distances from the nucleus, one farther will be easier to take. Because it turns out that ionization energy is also proportional to 1 over the distance squared. So small distance, large ionization energy, large distance, small ionization energy. Now these guys look like they're about the same distance from the nucleus because they go back to 0. So if we go back to that calcium, we have 2, 8, 8, and 2. These 2 are together, these 8 are together, these 8 are together, and these 2 are together. So these are different sets. So that's why ionization energies are interesting, is because just by looking at the sets of numbers, we can say, oh, these 2 belong together, but they don't belong with those 8.
Oh.
Huh. And why do these 2 make a line going back to the nucleus? Well, because they're about the same distance from the nucleus. Now, do you remember what the 2 ionization energies are for helium? We're supposed to look those up.
I have them written down.
Great. Try and find them.
Is it like the 2 enthalpy numbers you got?
Yep.
I guess I have 2,372 and 5,250. I guess
2,000 what?
2,372. But I guess if you round it to just 70.
So
2370.
Okay, so 2,400.
Yeah, 2,400.
And 5,300, right?
Yep.
And so if we actually plot that and we try to do a decent job here, so what I'm going to do here is I'm going to do this. So I'm going to call this 1 and this is 2. And 1, 2, 3, 4, 5. So this is a 2,000 and this is 4,000. Okay, so the first one would be at 2,400, which would be pretty much right there. A little less than halfway between 2,000 and 4,000, right?
Yeah.
And 5,300 would be somewhere around here. Now, if you take a look, these 2 don't really go right back to the nucleus, do they?
No, they just miss it.
But pretty close, right?
Right.
Okay, so these guys are equivalent, but they're not exactly the same. Are you with me?
Yeah.
Okay, so let's go back to the assignment.
They're equivalent just because they almost hit the nucleus?
Go back to helium. This is number 9.
Oh, right.
Go back to helium. You'll notice ionization energy 2 is not twice ionization energy 1. It's actually more than twice. I should say more than twice. I put more that twice. But you get the idea? This is more than twice 2400. Are you with me there?
Yeah.
Because twice is 4800 and it's 5300. So why does it take more than twice the energy to take this guy compared to that guy? Why isn't it 4800? And another question could be this. If this is 5300, why isn't this 2650, which would be half? Why is this guy a little easier to take than it should be?
Oh.
So here's how we do it. Which one is 1?
The down arrow.
And which one is 2?
The up arrow.
Okay, so here I'm going to do this. Since this is so small, I can do this. Here's number 1 and here's number 2. Are you with me?
Oh, yeah.
Okay. Why is 1 easier? Why is it 2400 instead of 2650?
Does it have anything to do with the neutral one being paired?
Right. This guy is giving the electron the shove, saying, hey, get the hell out of the orbital. So if that's happening, how much energy will it take? Will it take all 2650? And the answer is no, it takes a little less.
Oh.
Does that make sense?
It's taking a little less because it's paired?
Yeah.
Oh.
So you have to imagine that when they're paired, they repel one another. They repel one another. So imagine you have 2 electrons that are both in an orbital and one is being pushed by the other. Pushed where? Well, pushed nowhere because it's stuck in the orbital. But what if something comes along to take an electron out? Wouldn't it be easier to take an electron where the 2 electrons are fighting than where the 2 electrons are attracted to one another?
Yeah.
Yeah. That's why it's kind of that saying, divide and conquer, right?
Oh, right.
You'd rather fight 2 people that are fighting with each other than 2 people that are cooperating with each other. So the analogy is the same here. When you have 2 electrons fighting each other, it's going to be easier to take one out because the other one's going to help you take it away.
Oh, okay.
And then take a look at the second one. Is there any help from any other electron shoving that guy out of the orbital?
No, because it's an unpaired one.
Yeah. So here you got to pay the full price to take that electron.
Oh, okay. That makes sense.
So that's what's going on with 9 and well, I jumped over 8.
That's okay. Oh. Well, in terms of questions, that was it. Just
All
those
right.
ones.
What about 8? When you take a look at 8
Sure.
and you graph, when you graph a neon, you get this. 1, 2, 3, and 1, 2, 3. So I ask you to just graph the first 6 and you get something like that. Okay, so here, this is interesting here because if we look at neon, it's 1s2, 2s2, 2p6, and that's neon, right?
Right.
If I ask you to graph the first 10, and these are the first 6 of the first 10, actually the first 6, which one is this guy?
Is that, would that be in 1s?
Well, wouldn't you say no? They're the easiest ones. Wouldn't they be in the 2p?
Oh, wait. Oh, are they the easiest ones because they're near the nucleus?
Yeah, no. The easiest ones are farther from the nucleus.
Wait, but aren't those ones near the origin, which would be the nucleus?
No. See, that's the whole thing I'm trying to get you to realize here. This is not the nucleus.
Oh.
This is far away from the nucleus.
Oh.
If this is the 1s and this is the 2, or if this is the 1 and this is the 2 and this is the 3, which are closer to the nucleus?
Would it be 1?
The ones, because they're so darn hard to take.
Oh, I thought I must have got it. I thought the origin was near the nucleus.
No, so this is not the nucleus. The nucleus is over here.
Oh.
So here's the 1, here's the 2.
So is it if they're closer to the, so since the ones that are easier since they're farther away, is it the ones that are closer are harder to take?
Doesn't that make sense? Aren't electrons attracted to the nucleus?
Yeah, okay, that would.
So
okay.
are they going to be easier to take when they're closer to the nucleus and that attraction is great, or farther from the nucleus and the attraction is low?
It'd be easier if they're farther away.
It's just like magnets. If you have 2 magnets, isn't it easier to separate them if they're already separated a little bit?
Yeah.
But when they're touching, it's really hard because it's like they're close to the nucleus.
Okay, that explains it. That makes that. Oh, okay. I must have gotten it mixed up with the origin. Oh, so then yeah, so those ones would be the 2p ones since they're farther away.
Right. So which one is this?
Is that 1?
This is 1, 2, 3, 4, 5, 6. So if you look at neon, you see 2 sets of 3, but here we see 3 orbitals. What's going on here?
Wait, because I think, well, you said you graph 6, but in the question it says to do 8, I think.
If you look at the first,
because I think it says graph only the first 8.
Right. So here's the last 8. Here's 7 and 8. So you get a set of 3, a set of 3, and a set of 2. And I tell you, these are the 2s electrons.
Right.
So these are the 2p electrons.
So then would the first set be the down arrows and the second set be the up arrows?
Right.
Okay.
So the first set are the down arrows. The second set are the up arrows. And that's why there's only 2 sets in the 2p, is because you actually have 3 orbitals, and the sets are not orbitals. The sets are arrow up versus arrow down.
Oh.
Right? This set is arrow down. This set is arrow up.
Right.
And here, this is the easier one is the arrow down. The harder one's the arrow up. So normally when we look at these guys and you see 2 of them, you're thinking, oh, that's an orbital. But what happens when you see a set of 3? And the answer is a set of 3 would be 3 orbitals. What do you think D's look like? D's look like this. 5 and 5. This is exaggerated, but that's what D's look like because there's 5 orbitals.
Oh.
What would F look like?
Oh, how many does F have again? Is it 14?
That's right. So what would F look like?
2 sets of 7.
Yeah. The first set would be the arrow
down, and the second set would be the arrow up.
You got it.
Oh.
So that's what this whole lab is supposed to teach you guys about. It's difficult a concept to think about. And I'm glad we clarified what the origin is compared to the nucleus.
Yes.
It's far from the nucleus, right?
Yeah, right.
Because we expect electrons far from the nucleus to be easier to take.
Right. Okay. Those are the questions. That definitely clears it up with the origin, nucleus, and which ones are easier to take and which ones are harder to take.
Okay. How are you doing with the rest of the stuff in the chapter?
I get the stuff that I get, please. I get the doing the what is it, where you ask us to with the elements and saying it's 1s, 2s, all that kind of stuff.
Electron configurations?
Yeah, but I get all that stuff easy. But then looking at some of like the homework, there are a couple questions that are kind of messy.
Usually the tougher ones are the periodic trends.
I think it's also the yeah.
So there's 4 periodic trends that you need to know about.
Oh,
ionization energy, electron affinity, or they call it electron enthalpy something.
I don't know.
And then there's atom size or atom radius and ion radius. Those are the four.
Yeah.
So you need to know those trends.
Yep.
Let's cover those real quick, okay?
All right. Sounds good.
So for the trends, we're going to look at atom radius. Now, when you look at a period, they usually do this. So here they're large and here they're small. So when you look at fluorine versus sodium, or not sodium, fluorine versus lithium, lithium is large and fluorine is small. And that's really interesting because fluorine has 9 protons and lithium only has 3. How is it something with 9 protons and 9 electrons is smaller than lithium? And the answer is really simple. This guy's 1s2, 2s1. So here, this is going to help us understand the radius. This is 1s2, 2s2, 2p5. So this will help us understand the radius. What I'm trying to say is they both have electrons in the second shell, so that's going to really define how big they are. Okay?
All right.
All right. Now, if you have 3 protons pulling in a second shell versus 9 protons pulling in a second shell, who's going to do a better job of roping those electrons in and sucking them in, so to speak, and making the atom smaller? 9 protons or 3 protons?
Well, I guess just the videos, would it be 3?
Nope, 9 does a better job.
Oh.
Because it's 9 protons.
Oh,
right?
That, yeah.
This is like a big magnet.
Big magnet.
This is a small magnet. So who's going to do a better job of sucking those electrons in?
It'd be 9 protons then.
Okay. Now, on the other hand, when you look at atomic radius, so we're still going to stick with atomic radius. It looks like this. Here's lithium. Here's sodium. Here's potassium. This has 3 protons. This has 11 protons. This has 19 protons. So here, bigger protons doesn't mean smaller. Bigger protons means, or I should say more protons means larger. Why is that the case? This is 1s2, 2s1. This is 1s2, 2s2, 2p6, 3s1. So you're looking at a 3 versus a 2 for these. So in this case, we're looking at a 2 versus a 2. But in this case, we're looking at a 3 versus a 2. So what does having an extra shell of electrons do for you?
I don't know, just increase your size. But...
Right. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Here you're looking at a 4. So why is potassium larger?
Is it because it's it goes all the way to 4?
It's because it's got electrons in the 4th shell. Are you with me there?
Yeah, I'm with you there.
Okay. Now, when we look at more trends, ion radius, these are let me make sure I do this right. I'm just going to start over. When we look at ion radius, it goes like this, and then like this. And these are anions, and these are cations. So which are bigger in a period, the cations or the anions?
Would it be the anions?
The anions are larger. Without a doubt, clearly, easily seen. And do you see how the drawing in the book looks?
Oh, yeah.
So I've drawn just one row, if you will, okay? So why are these smaller and these bigger? Well, let's take a look at lithium versus, say, fluorine or fluoride. Well, this is lithium anion, and this is fluoride cation. Lithium anion is this, 1s2. Fluoride is 1s2, 2s2, 2p6. Why is fluoride bigger than lithium?
Is it because of the having the electrons in the 2s shell?
Yeah, well, not the
Or
2s.
2 subshells, sorry.
That's right. In the second shell versus, that's it. That's why anions are bigger.
Oh, because of that?
That's it.
Oh.
Do you see how every one of these anions is bigger than the cations? Every anion is bigger than the cations. Why?
Yeah?
Because you're talking different shells.
Oh. Oh,
Different
there's all in
shells.
the 2 shells. Or
Yeah,
2.
so it turns out that when you're trying to figure out what's going on with these periodic trends, you want to know the electron configuration.
Right.
And that's the tie into the previous part of the chapter. Because you said you were good at electron configurations, right?
Yeah, I get all that. I get the electron.
Okay, so now you know why you need to be good at it. Is because
because it can.
If the outer shell is different, that's going to lead to different properties. If the outer shell is bigger, it's going to be a larger atom. It's going to be a larger ion.
Oh, okay. That makes sense.
But here, if you take a look, this is oxide, 1s2, 2s2, 2p6. Notice the electron configurations are exactly the same. But oxide is larger. Why?
Is it? Well, I don't know, because oxide is in minus. Geez, I don't know.
Here's the deal. How many protons here for the fluorine atom? 9 protons. How many for the oxygen? 8 protons. Here you have 10 electrons. Here you have 10 electrons. They're exactly the same type of electrons. They're 1s, 2s, and 2p electrons. Are you with me?
Yeah.
They both have electrons in the second shell, correct?
Right.
So it should be a tie. Why is it not a tie? Well, take a look at the protons. Who has more protons?
Fluorine.
So won't fluorine be able to attract those electrons in better and make it smaller?
Oh.
Bigger magnet, right?
We can attract them, but why would it be smaller?
Well, I want you to think about this. Imagine you go to a concert and one person's got 10 people in the crowd. One group has 10 people in the crowd. Another group has 10 people in the crowd. You with me?
Right.
So imagine the more popular group, the one that is more attractive. What are those 10 people going to do? Are they going to get close to the band or far away from the band?
They're going to get closer.
Okay, imagine another band that is less attractive.
And
it's got 10 people in watching its performance. Are those 10 people going to kind of close in on the band, or are they going to mingle?
They're going to more spread out.
So that's the idea. More protons, more attraction.
That makes sense. Thinking of it like that makes sense.
Yeah.
Okay.
I just think of it as a magnet. A 9 proton magnet is bigger than an 8 proton magnet.
Oh, and then it would
and the
bring in
electrons
more
are pieces of iron being attracted to the center.
And they would be more smushed together than a weaker magnet. Okay. That makes sense. Yeah, no, using the concert example helps out.
That did it for you? And that's the same for lithium and beryllium. Why is beryllium smaller when it's still a 1s2? Well, lithium has 3 protons. How many does beryllium have? 4 protons.
4 protons. Okay. That, that band example really clears that up.
So that's why they get smaller going to the right. But you also have to remember that anions will be bigger than cations because they don't have the same outer shell.
Right.
So you'll notice that the 2 big reasons for why things are different is, first of all, if the N is different, that's the reason. So 2s, so 2 versus 3, 3 versus 4, 4 versus 5. If the N is different, that's the reason why they're different. But the second is, and here I'm talking about the outermost. Do you understand what I mean when I say outermost?
Is that what, like the 2s and 2p?
Yeah, biggest N. So biggest N is the outermost. Now, what if the biggest N is same? Then you go for number of protons in the nucleus. And that's usually the explanation for why things work the way they do. If you have more protons, you make yourself smaller.
Oh, right. Okay, that makes that makes sense.
But if you have different biggest N, that's the reason.
It's going to be okay.
Okay, so those are the reasons for these trends in order. So when you take a look at lithium +1 versus sodium +1, lithium is 1s2, sodium is 1s2, 2s2, 2p6. Why is sodium ion so much bigger than lithium ion?
Is it because it's in the because it's got the 2 shell?
Yeah, the outermost occupied shell. That's what they call it, outermost occupied shell. Occupied means with electrons in it.
Oh, okay.
So can you see why the 3 is not the outermost occupied shell? Outermost occupied. What does occupied mean?
Filled or something's in it.
There's electrons in it. There's no electrons in it.
Oh.
So 3 is not the outermost occupied shell.
Oh, so you would include the 3s.
So here's the outermost occupied shell. Here's the outermost occupied shell.
Oh, I get what you mean now. Okay.
You're looking at the number.
Right.
1, second shell, first shell. Why is the one shell not the outermost occupied shell in this one?
Is it just because the N is bigger?
Because there's electrons in the N equal 2. That's why.
Oh.
So here, if I give you this,
so it just transfer over.
What's the outermost occupied shell on this guy up here?
Is it 4s?
Well, how many electrons are in there?
Well, I can't really see it.
Oh.
It's a 0. So it'd be 3s2, wouldn't it?
So the 3 is the outermost occupied shell.
Oh, okay.
I'm not asking you for the outermost occupied subshell. I'm saying outermost occupied shell.
Oh, because it has electrons in it. Oh, yeah. Okay. I get that.
So it doesn't matter that the P is empty. What matters is that the third shell has something in it.
Oh. So even if you had like a 3d0 and the 4s0 and all that, just because the 3s2 has it's occupied, then that makes it the 3.
That makes the third shell occupied.
Oh, okay.
That's right.
Oh.
So when you start looking at size, here's n equal 1, here's n equal 2, here's n equal 3. If you have nothing here, then you look at the 2 to decide the size. But if you have something here, then you look at the 3.
Oh. All right.
If there's no electron there, it can't help make it bigger.
That's true.
which is like a double negative. I don't know if that works. Okay. The two other trends that you need to worry about other than ion is something called ionization energy. And that's the thing that you studied before that you were doing for the lab. So this is the energy required to remove the easiest electron. So if you have a 1s2, 2s2, 2p6, 3s2, that's going to be the easiest, the 3s. And why is it the easiest? Because it's the farthest from the nucleus. And why is this one the hardest?
Because it's closest to the nucleus.
Closest. That's right. Okay, and the number of ionization energies an atom has is equal to the number of electrons it has, which is equal to the number of protons it has. So there's ionization energy 1, ionization energy 2, ionization energy 3, all the way up to ionization energy Z, because if the atomic number is 15, there's going to be 15 of these. And remember, atomic number is number of protons.
Right.
Okay, so this is going to be the easiest, and this is the hardest. The first one is always the easiest. Now, when you look at ionization energies for when you look at ionization energies, F is, well, let me show you the chart. In general, F is going to be greater than oxygen. So why is that? And one way to justify it is this way. Here's the size of oxygen. Here's the size of fluorine. Remember how the radii go down when you go across the period?
Oh. Right.
The radii get smaller. Here's a picture of that. See how the radius gets smaller going across?
Oh, yeah. I see that.
Okay, so in general, this is the way you think about it. So why is this one harder to take an electron from and this one easier? Take a look at this. Which one's harder? Closest or farthest?
Closest.
Okay. Which one's harder? Closest or farthest?
The closest is floated.
Okay, so that's why fluorine is harder. You're taking away an electron that's closer to the nucleus.
But is...
Because here you're taking away this electron here, right? Versus this electron here. Which one's closer?
Oh. So is... But what is the... So does it have to do with anything to do with size as well?
That's what this is. This is the size.
So would it be a smaller size is harder to take away than a larger size?
Right. And why is this smaller? It's smaller because it has 9 protons and this has 8 protons.
Right. Okay.
So ultimately it goes back to this. Now, for fluorine, fluorine is more than chlorine. Now, why is that the case? Well, here's fluorine and here's chlorine. Why is chlorine less than fluorine?
Is it because it's oh, I was gonna say the period.
Closer,
Or,
harder.
right?
Farther,
Easier.
easier. For fluorine, you're taking a 2p. For chlorine, you're taking a
Oh, you're taking a 3p.
3p.
Oh, so that's okay. That's why that one's easier.
Yeah, so again, we're going back to, for ionization energies, what are we looking at? We're looking at
The
what shell are you taking it
configuration.
from? What shell are you taking it from?
And the size.
Yeah, and then if they're matched, then you look at, well, how many protons does it have? So do you see how the reasons are the same for ionization energy as they were for atom size?
Yeah, I can see that.
What are the two reasons? Reason one, different
N,
N,
and
number two,
is
same N,
but you go off the proton number.
Different protons. So what I'm trying to get you to think about here is the two most common reasons for atom size, ion size, ionization energy are the same reasons, different N or different number of protons.
Oh, so they're all just, oh, that makes it easier.
That makes it
just figuring it out. Yeah.
That's what it boils down to. Now, I'm going to be honest with you. Sometimes the trends are bucked. And I'm going to give you one instance of that with ionization energy. Okay. Let me give you the general trend though. If this is your periodic table, they say this is high ionization energy or large ionization energy and large electron affinity. We haven't talked about electron affinity. I'm going to leave that off the table. And down here is low. Okay, so I'm just going to leave that off the table, the electron affinity for right now. But I want you to think about this. If you have a large ionization energy, how easy is it to take an electron?
Do you have a low ionization energy?
High ionization.
Oh, high ionization. High ionization energy. Is it? Oh boy, is it? Would it be harder to take it? If it's
hard to take an electron. Now, when you take an electron from something, do you turn it into a cation or an anion?
Oh geez. I don't know. I guess if it's harder, would it be?
I'm not asking hard or easy. I'm just asking you, if you take an electron away, does the thing become a cation or anion?
Oh shoot. Oh geez, I don't remember the difference between them.
You can think it through. So a neutral atom has 9 protons.
Right.
How many electrons?
Wouldn't it be also 9?
That's right. Take one away, how many electrons are left?
8.
Okay, so when you take an electron away from something, does it become a cation or anion?
Would it become a cation?
That's right. So when you get into trouble where you don't know how to think about it, just do a hypothetical. So you take an electron, you become a cation, right?
Right.
Now these guys have large ionization energy, which means it's hard to take an electron. So if it's hard to take an electron, it's hard to turn them into cations.
Oh.
Now these have low ionization energies. So it's easy to take an electron. What does it mean about turning them into cations?
It's easier to turn them into cations then.
Now, electron affinity is the ability to attract an electron. So if you attract an electron, do you become a cation or anion?
Become an anion.
Okay, these guys have large electron affinity, so they attract electrons, so they
So
become
these-
anions.
Okay.
Do you
So
see how
these-
these actually complement one another? Large ionization energy means hard to become a cation. But large electron affinity means easy to become an anion. So do you see how they complement one another? Hard to be cation, easy to be anion.
And so it'd be the opposite for the low ionization energy and low
Right.
electron
It would
affinity.
be easy to be a cation, but hard to be an anion. And that's why when you look at your periodic table, you've got that break where these guys are the nonmetals, and the nonmetals become anions, and the metals become what?
Cations.
Cations. Why? Because these guys have low ionization energy and low electron affinity, and these guys have large ionization energy and large electron affinity. So that's what's going on there.
Oh.
I think we've probably done enough. What do you think? It's 112.
Yeah. Yeah, I guess you think so. So. Going up what you're saying.
What are you used to doing? 5-hour things or something?
Huh?
What are you used to? 5-hour Zoom sessions?
No, actually, this is the only class I have Zoom sessions.
How many classes are you taking?
I have four classes. Just the only time I do Zoom sessions in them is if I set up a meeting. But this is really the only class with a set day and set time for a Zoom session.
Oh, none of the others do, huh?
No.
And for these other ones where you set up a meeting, is it just you?
Yeah, just me and the teacher.
Wow. How does a teacher have that much time?
It tends to work out if it's the office hours or something. I've only ever really needed it with my math.
Math. Oh,
and one time with English, but he had time.
I don't know how you do math online.
It's not that bad. I had it over the summer. Luckily, I got the same teacher, so it's not been that bad, actually.
Good.
Yeah.
All right. Well, we'll see you on Friday. We'll be starting the next section.
Yeah. Well, this was actually a really good meeting. I got a lot of stuff. You helped me figure out a lot of stuff, so.
Good.
That's good. Yes. No, I definitely will see you on Friday.
Okay.
See you. Have a good rest of your day. Bye.